Hello everybody and welcome to this seminar on BS7671, the 18th edition, and in particular we're going to be looking at the data lines and the SPDs which are going to be inserted into data lines as opposed to the mains protection. My name is Rob Burnell and I'm the Market Development Manager for Dane UK Limited. So what we're going to be looking at are the surge protection devices for non-LV. So that's information technology, controls, comms, that sort of thing. So we're going to look at the sources of the surges, the standards that are going to apply, and the sorts of SPDs you would have in those networks or protocols. Now we start off with section 443 and 7671, and it is the case that if you have a lightning protection system, you will not be referring to any more parts of 443. You'll be diverted to 62305. Really, 7671 in its entirety is about the dwelling. Any other structure which is likely to have controls or comms, which is going to be more industrial or commercial, there's normally a lightning protection system going to be involved with that. So looking at 62305, what we see here is a structure. It has lightning protection, and we can see that 62305 overarches everything. We've got the four sources of damage, S1 direct hit, S2 the near miss, S3 which is a flash to a line directly connected to the structure like an overhead line, and S4 is a buried cable, a near miss to that. Now 7671 is only interested in the cables entering the building, whether they be overhead line or buried or LV or IT or comms and controls. But 62305 is responsible for everything. So that gives us a bit of a clue about the overlap between the two standards and where there's differentiation between your work as an electrical engineer and that work of the lightning protection company installer. A bit further in section 443 is this little bit about inherent overvoltage control. Now that's when you've got components built within to a piece of equipment which gives a level of overvoltage protection. That doesn't mean to say that you can do away with SPDs purely because the equipment's got some level of protection. It just means that you have to bear in mind that it's not just power going into a piece of equipment. It could be other services like a telephone line or some control line or something like that. We have to be aware of all of this sort of stuff in order to give a complete protection system. So here's an example. So we've got a domestic dwelling, and let's imagine we've got an SPD in the consumer unit. Now I know from my personal experience at a place I used to live in that I did have a SPD in the consumer unit. But then there was a nearby lightning strike on a house about 200 meters from where I live. And this looks pretty much like my master socket looked like. So yes, it was a bit charred and it completely blew up, and you can see that situation here. And also we had a situation where the telephone itself was blown to bits. Same for me, and also the microfilter and the router that was taken out as well. Now I was offline for a few days while BT had to come along because naturally they have to make an appointment to get into my house. And that one lightning strike in the village where I lived, that took that guy about 2 weeks to sort out the 20 odd buildings which had been affected by that strike. And I'd imagine it'd be a similar case for this one as well. And here we can see a slightly larger telephone system. Now, this is typical of, say, a small business or a retail unit, something like that. And we can see just about that there has been some damage. So we can see the printed circuit board is blown to bits. Where the cables come in, that's looking very charred. Now, this business is going to be offline. Now, the cost of replacing this unit may not be a huge amount, but it's the downtime. That's what's really going to cost the money. And this is what you have to factor in when you decide, yep, I'm going to have SPDs or not. It's not just the physical thing that you're replacing. You have to think about the disruption to the service as well. Now, here's a washing machine. And we can see here that components are damaged. This is a result again of a nearby lightning strike. And yep, that could be a new printed circuit board. Maybe that's worth doing, maybe it isn't. Maybe it's just worth buying a new washing machine. In any event, you're going to be tempted to claim on insurance. And the way things are at the moment, yep, I think the insurance company is going to pay out on the first one, And then they're going to say, do you know what? We don't want to pay out again. Now you have to fit the SPD. So fitting them whenever you're having some major works done or a new board, that becomes a very sensible idea. So once we've decided that we're going to have SPDs because section 443 requires it, or 62305, in either event you go to section 534, which is how we actually fit them. And in the introduction to section 534, we have a couple of documents which are frequently mentioned: 62305, the lightning protection standard; 61643, which is the surge protection product standard. Now, all of these documents, including 7671, describe the application and installation of SPDs according to the lightning protection zone concept, or LPZ. And as we can see there, that describes the installation of type 1, type 2, and type 3 SPDs. Now, what the LPZ zones look like, it's fairly straightforward. LPZ0 is the external, that's the sky, that's where lightning is, that's the most dangerous zone. LPZ1 is the entire volume of the structure that has got the lightning protection system on. And LPZ2 is a screened object which is within the building. Now, strictly speaking, when you think about a dwelling, you're coming from outside, zone 0, straight into zone 2, in fact, because your cable terminates in a consumer unit, which is going to be metallic, i.e. screened or shielded, and that's where you locate your SPD. So in dwellings, you're pretty much bypassing LPZ1 anyway. But in larger installations, you will certainly have at least LPZ1 and 2, maybe more. But the basic topology is outside is LPZ0, inside is 1, and a distribution board or control panel, that'll be LPZ2. So looking at it in a sort of more holistic way, in this illustration, we can see the overall picture in terms of the LPZ concept, where we see LPZ0, but now it's been subdivided. LPZ0 is subdivided when you have a fitted lightning protection system. And because this is an isolated system, which is involving masts and pointy things to protect the objects on the roof, as opposed to just cross-bonding everything, I effectively now have an LPZ0A, which is beyond the protection afforded by the LPS, and LPZ0B, which is underneath that umbrella of protection afforded by the LPS. And you can see those arcs on the roof, that's the rolling sphere as it sort of went over the roof to establish where the LPS was going to be fitted. So the external zone has now been subdivided into protected and unprotected. You can see that LPZ1 is the entire volume of the building. Any screened metal object, control cabinet or distribution board, that's LPZ2, which is within the structure itself. And then you can see in there's a tiny LPZ3, which will be at a PDU, which is in LPZ2, which is a screened data center room. So the topology in certain buildings may change a bit. So in certain sites, you can have well beyond LPZ3, especially on certain military sites or certain data centers. So we're going to start looking at some typical, what we call transition zones from an external line to an internal area. And some of this will be LV, as in, the location of the main distribution board, but we also have telephone lines coming in. So wherever we have a cable crossing a zone from the external to an internal zone, yes, I'm going to have my main power SPD and the main distribution board, and I will have them on the BT lines coming in. And the thing with some of these slides is that the appearance of the SPD may change because of the application, so don't get too hung up on that. And you'll also see that, again, as I said before, it's not from LPZ0 into 1. The metal box is a further zone within the volume of the building. So looking at another example now, and in this particular case, we're going to look at a very common application, which is CCTV. So the CCTV is outside, it's external, so it comes from 0B because it's underneath the protected area of the actual installation. And we will have power perhaps go into the camera, and we will certainly have a data line or a video line. And in fact, it could be a BNC connection or an Ethernet connection. But in any event, we would be interested to stop the surge coming from the external into the structure, and especially we want to protect the recording equipment. It's sometimes a moot point. It depends on the containment of the cable, whether we're interested in the influence of a surge going down the cable, but whether we put them here and at the rack, i.e. the recording equipment end. Now we're going to look at another application. And in this particular case, this is a very common one. I've done quite a few of these recently, where we've got an MCC, a motor control center, controlling all the plant on the roof. And this will be typically installed on a level below the roof line, though on an external plant room, that's another example. So we're coming from a protected area within the building, so it's LPZ1 to 2. Now in many installations, as you can see here, it is not uncommon for a panel builder to produce a bog standard control panel for a typical application on the roof. So he's got all his controls, all his equipment, and all the other sort of gear. And then there's an add-on unit. So as the cables come to and from the roof, they will go through this SPD section before they carry on to where they would normally be expected to go. Because the surges are not going to just go down the power lines, they're going to go down any conductive cable. So that's your controls, your comms, anything like that. And all of those cables, you have to think, if that cable takes down a piece of equipment, which means my air handling unit stops, and that's catastrophic for my data center, then it's going to need some form of protection. So looking at another example, and this one's particularly interesting. So this is a satellite dish. Now in this case, this is an isolated lightning protection system. How do we know? Well, it's bolted, that is the dish is bolted to a GRP post. And what we see going up on the right hand side is a small round lightning conductor. So that disappears out of shot, but the lightning will hit that. It'll go down the lightning conductor on the right. The GRP pole is not energized. Those standoffs, they're not metallic, they're insulated as well. So that represents a separation distance, so there's no flashover. So what this means is the lightning cannot actually hit the dish. Therefore, I would not need type 1 SPDs on the coaxial cable from the outside, which goes down into, say, a communications rack or something like that. So if I have an isolated system, it does away with the need for SPDs. So you're going to be encouraged as a lightning protection contractor to have a conversation with all the other trades. And that works the other way around as well. So the guy that's fitting up the satellite dish, he may not actually be happy with lightning hitting the dish. It might be a critical service that needs protecting. So an isolated lightning protection system would go a long way to solving those problems. So just to clarify that, now this comes from another standard which the aerial installation industry uses, that's 60728-11. Now that's new, and it does follow exactly the same message as 62305 and 7671. So in this illustration, we have a clear modeling here of the separation distance. We've got the angular protection, so lightning cannot hit the dish. Therefore, I only need to fit type 2 SPDs because there's no chance of a direct hit. In this picture, however, which is typical for installations, the copper tape, which you can just about see on that plant room, is cross-bonded to all of the bracketry and the dishes, so that is a cross-bonded system. What this means is the whole of the metalwork will be energized. What's attached to the dish? A cable, and that cable's going in somewhere to a comms rack or something like that, and because it's cross-bonded, you are forced to use type 1 SPDs or type 1 combination 2 SPDs to protect the distribution amp and stop any chance of flashover inside the building itself. And again, the BSCN 60728-11 would refer, and it's exactly the same message as 62305. Just for information, that's what happens if lightning does hit a dish. So there's not much left, to be honest. Now, in a domestic dwelling, can you stop this sort of thing from happening? Yes, you can, if you really want to. Let's not dwell dwell on it too much. It is a very, very rare event, but it can happen. So back to our overall diagram. And what we're looking at now is the application of SPDs, as we just mentioned, on the actual coax. And we don't need a type 1, type 2 SPD, just a type 2 is enough because we have an isolated protection system. And then having a further deeper look in the installation, we're now very much deeper in LPZ3, which is the PDU in the data center. We've already had some surge protection at main distribution and sub-distribution boards. This is end-of-line individual equipment protection. So we can see a small type 3 SPD on the mains, and if required, we've got some data line SPDs because we may have crossed a transition zone of LPZs within the building itself. So when we look at the regulations in 7671, it's this regulation 534.4.1.2. This is the one that's going to catch you out. In accordance with the LPZ concept, and that's what we've just been looking at, where a cable crosses the zonal interface, further SPDs shall be installed to preserve zonal integrity. And this makes perfect sense. What's the point of having a structure which has got external protection, so you've done a good job of protecting it from the effects of a direct hit, and then you bring a cable from the outside in? That's a hole in the Faraday cage. So that's the bit that you actually have to cover using your SPDs. Then in section 534.4.1.6, there are these other points we have to look at. And there's the second one down there, the second indent. Overvoltages on other incoming services, such as metallic telecoms and signaling services. And I may have, in the next indent there, secondary buildings. I'll have services on those. External installations. I may have external sensors. And the wording here is quite key. These SPDs shall be installed and located as close as possible to the origin of such events. As I said, that's where the cable comes from the outside in. You have to nip the surge in the bud at the origin of the event itself. So here's some examples. So I've got a building on the left-hand side where I've got power coming in, SPD, controls coming in, fit the SPD there. And on the other ones, we've got two buildings which are linked by power. There could quite possibly be a common Ethernet loop. If it's fiber, we don't worry about that. We don't need SPDs on fiber. But if there's any copper comms cables between those two buildings, they would have to be looked at as well. So what we've just seen and heard there is what happens during a lightning strike. And there's a theoretical radius of 2 kilometers. That's where the effects of any direct hit onto the ground can be felt. And that would mean that the sort of kV per meter would be appreciable for up to 2 kilometers away. And that would have an impact in any buried cable, whether it's LV or TV, telephone lines, whatever. And it's not just the direct hits we're interested in. It's all this, as I say, collateral damage that can be just as impactful on an installation. So we're going to have a look at the types of SPD now. We're going to have a look at how it all interfaces with the regulations. As we know, in LV there is the type 1, type 2, and type 3 SPD. For data lines, we have something a little different. We still have 3 types, but it's all terminology. So let's imagine we've got our installation. So we've got on the right-hand side our power coming in, and on the left-hand side we've got our data lines coming in. In accordance with 62305, because we have a lightning protection system, we need a type. We've got the rolling sphere, we've got the capacity for direct hit there, and we have our earth. So on the right, I've got my type 1 SPD that takes the lightning currents down to earth onto the MET. And then on the left, you can see that we have a type 1 and the letter D and the number 1. A D1 is for the data line. It also applies to controls and comms, but that's the way that these are actually described. And then when we get to type 2, so on the right hand side I've got a type 2 SPD on the power, on the subdistribution board, and on the data side on the left there I've got a C2. Don't ask me why they're called C2, they're just called C2 for type 2s. We get to SPDs very close to the sensitive equipment. On the right hand side I've got a type 3 SPD. On the left hand side I've still got a type 3, but it's called a C1. Yes, that doesn't make any sense either, but that's how they're described: D1, C2, C1. And what just popped up there is typically the lightning current for the type 1 is only 2.5 kA, 10/350. Type 2 is 5,000 amps, but that's 8/20, and the type 3 is about 500 amps, and again that's an 8/20. That's nothing like the 25 kA for a type 1 on the LV side. Why the difference? Well, simply because the cable sizes for, say, an Ethernet cable are so tiny, you're not going to pass 25 kA down them. It's going to act like a bit of fuse wire. So these are the categories. This comes from 61643. So when we're looking at the type 1 SPD, that's the D1, we can see that we've got short circuit currents of 500 amps, 1 kA, 2.5 kA, rated at 10/350. For the type 2, we got the 1 kA, the 2 kA, and the 5 kA, 8/20, surges, and the type 3 is 250 amps and 500 amps, again at 8/20. So that's the typical current ratings for the data line SPDs. Now we're going to have a look at the general design of these data line SPDs, because they're not the same as the power. We have different components. Now the most robust one you would typically find is a gas discharge tube. It doesn't have any leakage current. That's a good thing. It has a high discharge capacity. That's also a good thing. The only disadvantage is a slow response time. It's a bit like trying to strike a fluorescent tube. It takes a little bit of time for it to strike up, but once it's become a short circuit during the surge event, you're away. The Varistor, very common device, especially in the mains voltage, but again they're very handy in the data line type of SPD. Medium discharge capacity, very quick response time, but there is a leakage current. That's why you can't use these on a TT system, because of the leakage current, where you can get nuisance tripping or a very dangerous situation. And then finally we got suppressor diodes. Now these are particularly quick. They have very low leakage currents, but they don't take a huge amount of energy before they go bang. They are typically used in conjunction with the other components. So you've got the high capacity of the gas tube, but you've got the fast reaction time of the suppressor diode, and that would give you an overall sort of SPD. So if we build up a design, we would have at the front end our sort of type 1 component perhaps. That could be the course protection, but that might let through a little bit too much energy. So we would have the fine protection of the fast acting diode, but the trouble is we have to coordinate the two. If the output of the type 1 or the course protection, the gas tube, is too much, we end up destroying our own component. So that's when we have to have some coordination, and this is true of any sort of SPD circuit. So this decoupling or coordinating component will introduce resistance, inductance, or capacitance, so that when the type 1 operates, that gives me coordination with the more sensitive objects further in the SPD housing, so they act as a coordinated circuit. Now the way that we illustrate this within our catalogue is with this sort of terminology, or symbology rather. So the type 1s have a little key, and the corresponding type 2 or type 3 SPD that the type 1 is compatible with has the lock. So you put the key into the lock. That means you have a combination arrangement so that you have the high discharge capacity and the fast response time. And that's one of the features you will notice in certainly our catalogue. Other manufacturers may have other ways of showing this. So as an example, when we're protecting a BT line, I would have the 10-way, it's shown here as the DRL 10B180. So that goes across each of the 10 lines in the BT chrome block or LSA strip. And you can see it's marked up there as a type 1 with that shape on the designating symbol there. And if I want to fine tune the circuit because there's still too much energy going through, I will select a component which is a type 3 device, which goes into a rack, which plugs in top of the type 1 SPD. So I can have a combination of type 1 lines and type 1 and 3 lines all in the same housing there. So I can have some coarse and fine protection per line if I wish. In addition, we also protect Ethernet lines. So you can either have an RJ45 connection in and out, and the earthing arrangement is via the metal chassis to the DIN rail. And in another case, we have an SPD which has already got cables pre-made. So you just have short connections within, say, a 19-inch rack arrangement in your hub. It's very important to consider this. As you can see, Ethernet cables are susceptible to surge, especially from external components. So you need these SPDs to protect telecom systems or any other sort of IT arrangement. They're easy to fit. They're just a plug-in arrangement. They can fit into data cabinets or on DIN rails, and they would protect all sorts of external equipment. And there are sort of various approvals and standards associated with those devices. So an Ethernet SPD can be mounted right by the rack, or it can be very close to external equipment. So here we've got an internal SPD designed to go into a rack. And we've also got a watertight SPD, which is designed to be pole mounted for, say, access points or repeaters or something like that. So when we talk about external Ethernet applications, it could be a repeater Wi-Fi panel, an internet camera, an IP CCTV, anything like that. Any cable coming from the outside, you don't necessarily want a surge appearing at the hub, which would then enable it to distribute that surge throughout your whole installation. That could be very damaging. And here's an external SPD. So it's mounted on the outside. It's IP66, completely watertight. And you just take your RJ45 cables into the bottom. So you've got an in and an out. And your protection is there for the camera and to stop it transmitting back into the network. And similarly, we have them for CCTV, not the BNC connection. So again, it's either mounted under the back of the recorder, sort of a loose fit there on the cabling, or mounted onto DIN rail. And we can have them with what they call direct or indirect. So you'll be protected from any other nonsense on the earthing system. The separation is achieved using a gas tube to give you isolation from the earthing system. Now, there are other versions of CCTV. So you can have all in one SPD, both the BNC video, the RS485 control for the power tilt and zoom, and then the power for the actual unit itself. So you've got a combination one. And another version for external applications would be public address, tannoy speakers, that sort of thing. So if there's a situation at a military site or a shopping mall, you would want these safety circuits, these public address systems to work. So we have some specific SPDs just for these applications. And here are typical applications. So they're all mounted outside, they're all on poles, they're all likely to get zapped by lightning, and this is why we have these new developments in SPDs. Now, as you can imagine, there's quite a few applications in data line, far more so than the power ones. With the power, you've got like three-phase, single phase, you might have TT, TN. It's a lot simpler on the power side of things. When we get to data, we have to be mindful of the nominal voltages, and then we have to be mindful of the current that's expected to be present. And then what sort of bandwidth, what frequency are we going to be looking at? All of these things are factors in SPD selection when it comes to the data side. To help, we do have online selectors, and we have it in a printed material. So if you've got an idea of what the communication protocol is, or the actual, whether it's Profibus or Ethernet, Modbus 485, there's a whole range of different types. We have selection guides to help out. One of the other things about data SPDs is looking after them. Unfortunately, it's not possible to get feedback from many of these SPDs. It's not like the green is good, red is bad on the power. So let's have a look at the maintenance strategies. First of all, we got a handheld tester, and there are a couple of models. There's the bog standard one, which you can just hold over the SPD itself. That's with SPDs with this feature. It's called Life Check. And you hit the test button and it either gives you, yep, that one's okay, or it isn't, because you can't tell by looking on the SPD itself. Another version of this is, again, a push button arrangement, and this time you save the results in the actual device itself, where you can download them via an interfacing cable. So you can have a basic tester or a more bells and whistles version. One of the other ways of also doing this is to have a master-slave arrangement. So looking at this, we've got a selection of yellow data SPDs, and then we've got some intrinsically safe circuits with the barrier there. But in the middle of that lot, there is a grey slice. And that grey slice will check in with all of those SPDs one at a time in a cyclical way, and it can monitor in blocks of 10, and you can have up to 15 of these blocks. And that way, if any one SPD fails in that block of 10, the master unit will record that and send an output to a centralized system saying, hey, at this location, this SPD has failed, which is very useful to know. So here's a bit more on the actual live check. I've got the tester on the right-hand side. I've got the surge protection unit, and in between is the reader. And that's going to check in with the SPD to see if any part of the SPD has been stressed by a surge event. And if the results fall outside some parameters, that's when I start to get a pass or fail sort of feedback. Inside, it's all done via RFID communication, so it's no contact. There's no intervention, so I can just check it remotely. So there we go. In practice, it says they're in contact, but so long as it's there or touching or within a millimeter, I will get feedback from that particular SPD. I can even unplug it. This could be very handy if I'm in an intrinsically safe or an ATEX environment, where I obviously can't take the tester into that sort of environment, so I can remove the testers, rather the actual SPD plugs, then apply the tester, and then I can go back into that environment without introducing any threat from the tester itself, because it's not ATEX approved. Now, the normal maintenance regime with SPD is to wait for it to fail. So once the SPD has failed, I then replace the SPD, and then it's business as usual. So there is the possibility of some damage occurring, and that's a problem. So with Live Check, it gives me that much more proactive and preventative maintenance regime. So if I get an SPD which is indicating that it has suffered some stress, now I can at least get on ordering it before it fails completely. And now we're going to have a bit more look at that. So with the master-slave arrangement, as I said before, we can have indication on the front of the unit as opposed to the front of the SPDs, and I've got remote indication via this fault-free contact. In addition, on certain units, I can have a communication interface, so I can interface it with a PC in part of a larger building management system. Again, it's working in pretty much the same way. So I have data within the master or reader. I'm getting information from the SPDs either side, and that goes through the RS485 interface, and then it gets transmitted via a USB connection into the PC. So looking on the front, if everything's okay, it's going to be green, just like SPDs normally are. During the actual testing process, it'll flash yellow, and if one of those SPDs flags up as being defective, it'll flash red. Now, normally in a block of 10, if it flashes 4 times, that tells me that SPD number 4 has failed. So when I open the cabinet doors, at least I know which one I need to pull out, because it's not obvious, as I said, just by looking at them. So when we're looking at the display as part of the PC package, the same thing will happen. Any healthy SPD is going to be green. Any that are defective are going to flag up as red. I know where the location is. I know which SPD is. So when I send a guy out to sort it out, to fix it, he knows exactly what SPD plug he needs to be carrying, and he can just simply swap it out there and then. Very easy to do. And I don't lose the line as a matter of interest. Comms is my. So it's very flexible. I can have obviously more than just 10 SPDs. I can have multiple masters with a common loop back, and that also helps with the PC monitoring system. So I can daisy chain these monitors to up to 150 SPDs. Very useful and larger data hungry installations. And there's a screenshot there of the status. So I will populate that in the beginning. I can give them an identity, and I can give them location, and that can be part of my overall monitoring package, say on a sort of water treatment plant, biomass or anaerobic digestion or something like that. Oil, gas installations would benefit from this arrangement. So now we don't wait for things to go bang. We actually have a more preventative sort of thing. So if we detect that one of the SPDs is beginning to fail, which we would detect, there would not be any damage because we replaced the SPD before that damage can happen. In common with the power SPDs, there is a changeover contact. The master arrangement on the data SPDs has that facility as well on the master unit. But what about those other devices like the video or the Ethernet, where there isn't this arrangement either? Well, on all of our data sheets, it is possible to test the SPD using a meter. You may have to knock up a little fly lead to go from signal to ground. So if you get a high value, that's great. That's what we're looking for. If you get a dead short, that means the component has failed, and you can take it to recycling and deal with it appropriately. And then we're getting smarter. We actually have these new monitoring arrangements which will allow you to use an app, and you just sort of scan the barcode or the QR code rather on the SPD, so that'll populate the number of SPDs within your system onto the app, and it integrates into an Ethernet network. And once you involve the Ethernet, you can go to a cloud-based system. So I can now monitor the changeover contact on power SPDs and a whole range of data lines, up to I think 150 data lines can be monitored with this new cloud-based app-driven arrangement. Now we're going to have a look at a typical structure and using SPDs within that structure, sort of real life applications. So in addition to the LV network, we could have some coaxial on the roof, maybe satellite dishes, maybe FM. And if it's all going to be cross-bonded, which would be typical in the UK, we'd have to have type 1s up the roof line. And then when we get down to the ICT racks in the basement, I would protect them locally with a type 3 on all those coaxial lines. The type 1 is going to be there to protect the roof mounted or the much higher up distribution network. And then we get to the telephone line. I may indeed have fiber coming in, not interested in that. But if I've got these BT lines coming in, however many 10-way blocks need protection on the the incoming lines, I would plug in one of those Crone units. And then if I've got some specific lines, further in the installation for like refuge points or telephones within lifts, which I want to keep working, or associated with an alarm panel, I can have sort of localized SPDs at those other locations as well. And then when I've got plant on the roof, so I'll have a plant room, I will have cables from the plant room going out to roof mounted equipment. I automatically know that when any cable leaves that plant room going onto the roof, it'll need an SPD. So here we'll see the coaxial, we'll see the power, of course, for the plant, and then it's going to be controls, comms, sensor lines, and all of them will have to be type 1s because in this arrangement, certainly, it's going to be a cross-bonded system, so they will need to be type 1 SPDs. And this is going to illustrate why we need type 1 SPDs. So lightning hits the plant on the roof because it's cross-bonded, and because there is continuous metallic ducting coming into the installation, the ducting which is providing the ventilation in the server room at the bottom, that all becomes energized, and any cabling associated with that ducting is going to have an influence because of those energies flowing within the metalwork. And that's why we need so many more of these SPDs in the data lines. And the same goes for any other plant on the roof which is cross-bonded. So on a metallic roof or a metallic structure, any of these air handling units, yes, I'm going to need an SPD in the isolator for the power, but I'm going to need also the controls and the comms for all of these external units to be protected as well. And as you can see, that may indeed involve a lot of SPDs because of the sheer number of cables which are leaving the roofline and coming into the plant room. So here we have a structure which has got a network system inside. It's got lightning protection on the roof, and well, lightning hits the roof. The lightning does what we want it to do, which is it goes down the conductors into the ground, but also the mesh on the roof is energized. And any cable within influence of the mesh on the roof or the conductors will have a small induced current going down those cables, which could take out the rack mounted hub or switch. And then if there's a nearby lightning strike, any copper cabling in the vicinity of the building which goes into the building will bring a surge into the building. And as I said before, if it's fiber, we're not interested in that. So that's why we have to have these SPDs to cover from the effects of a direct hit and near miss. Now, if we had a different lightning protection system on the roof, the isolated system, then things do look a little different. So I have exactly the same presentation here as I did a couple of slides ago, where I've got an air handling unit. I have got continuous metal ducting going into the structure, which is cooling the server room and the other sort of trading floors, perhaps. All of those PCs generate a lot of heat. So lightning hits the mast, not the plant, and the lightning is conducted across the roof, down the sides into ground. We keep the lightning on the outside with an isolated system. That means that those SPDs on any roof mounted plant don't have to be type 1. There's a massive cost saving associated with that, and less stress on the installation. Now, unfortunately, there's only one tick box in 7671 in the model forms where you record whether there are SPDs or not. So you just tick the box. Is there an SPD, yes or no? It doesn't really make an allowance for the sheer number of SPDs you're likely to come across. So in this installation, it's fairly easy. I tick the box that there's an SPD fitted. I can tick the box that it's a type 1 if necessary. I can tick the box if it's got the overcurrent protection to match the Ka value of the SPD, and I can tick the box that the cables are the correct size, at least 16mm because it's a type 1, and they're within the 0.5 to 1 meter rule within the standard as well. So it's not just one tick box, even for one SPD. So let's imagine an installation where I've got AC coming into this cabinet. So there's an SPD. I've got DC going out to a pump. after that rectifier inverter arrangement. So those cables are going out to field equipment, so they have to have an SPD. And then there's going to be some controls or data going out to the pumps, and they will need an SPD as well, because this pump is critical. It must keep working. So all of the cables which leave this cabinet or leave the structure and go outside will have an SPD. And I will need to know that the cable length and size and the fusing for all of these circuits are okay before I can tick that box. And then in other parts of the installation, I may have CCTV, and here we can see the rack equipment, and I can see a row of BNC video SPDs, and the earth is taken to an earth bonding point just out of shot. I can see a control cabinet, and I can see that there are additional yellow SPDs from other external control locations. And then I can see the fire alarm panel, and that yes, there's an SPD there, and that's a type 3 wired across the main incoming terminals, and the SPD has a black disc on it. That's a buzzer, so if that SPD fails, it's going to scream its head off. And again, I can only tick the box once all of these incoming lines from external locations have had the SPDs fitted. But that's it. That's really been a focus on the data lines. It does pretty much follow the requirements of 7671 as you would do for power. But if you have any questions or need any more information, please get in touch with the Dane UK office. Thank you very much for your time.